do that. So for DC circuits, we have Kirchhoff laws first, and Kirchhoff has two basic laws. First one is called Kirchhoff's first law. Usually it is also sometimes given by or written as the current law, like that. What it says is way two important things that you need to basically write. Number one, the sum of all currents entering any point in a circuit is equal to the sum of currents leaving that same point. What I mean by this is, for example, there is a point where a couple of wires are attached to. This one is taking 2 ampere away, 3 amperes this way, 4 amperes. This is what we need. This 0.5 and this is 1.0. So what you should remember is that the sum of currents entering would be basically, this is the junction, so 3, 1, and that's it, right? Also equals to sum of currents exiting, which means that 4, 2 and 0.5, they're all going out, as you can see from the point. So if you add them up, I should come out to be 2.5 amperes. Is that clear, everyone? Yes, Hamad, do you understand? Aman, Aisha?
Yes.
Good. Now, with that said, then we need to know what this basically, this particular law depends on what principle. So, note first law obeys law of conservation of charge. That whatever charge is basically going to enter, the same amount of charge is going to exit. Charge cannot be, just misplaced in the middle, right? Like that. Please write this down and see if you have a question. All right. Now, the next thing is the Kirchhoff's second law. It's also known as the voltage law. All right, so that's two names. Now, it also comes for 2 marks, so we're going to write it. That's what it says is the sum of the EMFs around a loop in a closed circuit, so 1 mark, is equal to sum of potential differences around that loop. Now, which basically means that whatever energy is going out is whatever energy we basically gave in the circuit, the same amount of energy per unit charge is going out. Now, for example, a loop sort of like this is given to you. Like that. And they say this is the EMF E1, E2, E3. This is R1, R2, resistance R4, and R3, like that. So if you notice, the positive and negative terminals are here. And suppose they've shown the current is going here, or you could assume it yourself. So we know the current is going to go in this loop like this. So this is a closed loop. All right, we're following right now. Now,
circuits roll up a little bit.
yes.
Okay, fine.
Okay. Now, it's a sum of EMFs is equal to the sum of potential differences that was given to you in the question. Like, this is what the law is. So basically there are three. If you notice, E1 and E2 are connected correctly, one after another. So we're going to write E1 plus E2. But actually, the positive terminal of E2 is connected with positive terminal of E3. So E3 is opposing the current. It's not correctly connected in the same direction, which means we're going to put negative E3 because it's opposite direction. And then the potential difference across R1 will be current into R1 plus next one is current into R2 plus current. Same amount of current is going in R4 plus R3. Do you guys understand? Please let me know if you have a question here. Check the equation, see if I've done it right. Now, please write this note that second law obeys law of conservation of energy because it's talking about energy per unit charge, which is voltage. All right, Aman, Aisha, Khatija, Hamad. Any questions, please? Everybody's clear about it?
एक बार से repeat करना पड़ेगा second.
Okay. If you run your finger through this point, right, Hamad? So you'll see that E1 and E2 are connected exactly with how it should be, like positive should be connected to the negative and so on. Or they're in the same way, right?
Yeah.
So when you reach E3, it is basically opposite of the direction of current, right? So you're following that. So then it means the current needs to oppose it, which means that because it is opposite, so we have put it as negative E3. Do you understand? It just means that it's not in the same direction as the flow of current. Understood?
Yeah.
Now, the next thing is that because potential difference we can find using current into resistance. So all the energy that's going out around the resistance are, because current is I in the circuit, so it will be I times R1 plus I times R2 and so on. I times R3, I times R4. So you add all of those and then you're gonna get the EMF. Understood? The total potential difference. So basically you just need to add the batteries together and all the potential differences together, like that. Okay? Alright, is that clear, everybody? Should I go forward then? Okay. Now, the next thing we're going to do, basically, Kirchhoff laws enabled us to find or work on series and parallel circuits. Now, series circuit basically means that with a cell or a battery or any source really, the components like resistors or bulbs or whatever they are connected one after another. So if this is the EMF E, so this is resistance R1, R2, R3, and the current is I. So each one of these will have voltage V1, V2, V3, like that, right? So the idea about a series combination is that the current in each component stays the same. Whatever the current is in the circuit, it will go through all of them with an equal quantity. However, the voltage is divided, which means the total EMF is equal to voltage 1, voltage 2, or potential. So basically this is the same Kirchhoff's second law that we just studied, that the sum of EMF is equal to sum of potential differences. And then from this point onwards, this whole thing that we are doing is a derivation that basically is required, usually 1 or 2 marks it is there. So now, since we know that EMF can be written as current into R, IR, this is I times R1 plus I times R2 plus I times R3, because voltage is current into resistance. So I is same, so it will be cancelled. So the total resistance that can be found in series is by simply adding the number of resistors in series. So that's what we need to find. Is that clear? Aisha?
Yes, sir.
Khatija, everything is clear? Khatija, mic?
Yes, sir.
Okay, good. Now, for parallel circuit, it basically has like each branch is dealt separately. When I say branch, basically branch means a point from here till here where the connection is. Now, so if this is the EMF, this is R1, R2, R3, this is V1, V2, V3. So what I want you to understand is that in parallel, voltage is same across each branch. What I mean by this is that whatever right now it looks like the EMF is equal to VI equals to V2 equals to V3. All of the branches are getting the same voltage. Now, however, when the current basically comes in, like it goes out of the battery, it needs to decide how much it wants to go here depending on the resistance, right? So the higher the resistance would be, current would be lower in that branch. But generally what we can say is that then the current is always equal to I with the sum of all current. This is the Kirchhoff's. So the current entering, this current is entering this junction and then splitting into 3. So it means that the current that is entering should be equal to the current that is leaving. That is the reason this is the equation, and we've learned it in first law. Now, because the total current will come out from voltage over total resistance. So I1 will be equal to voltage over R1 plus voltage over R2 plus voltage over R3. So the total resistance will be equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Because voltage is the same, that's why it cancels out. So basically in parallel, the resistances are added by the reciprocals, and then you have to take a reciprocal at the end as well. Okay. Let me know if you have a question, please.
Yeah. Maria has no one contacted. तुमने करना था उसको contact. सवा 5 बजे क्लास थी तो तुम अब कौन क्या कर
Alright, please write this down. Alright. Is that clear, everyone? Alright. Now, so let's basically try and solve a question. So basically this is the same as O levels that we've already done. For example, a circuit is given to you like this. In 10 minutes when the link expires, okay, you need to rejoin, please. And then okay, I need to make it bigger, sorry. And suppose a complex circuit like this is given, right? Now this is like 40 ohms, this is 20 ohms, this is 60, this is 40, and that's 96 ohms. Okay. Now, first of all, in this question they say show that the network of resistors have a total resistance of 40 ohms. Alright, so this is basically given to you. In the second part, it says calculate the current in 60 ohms resistor. Now, these sort of questions will be like there all the time. So what you guys need to remember is that you need to basically do them again and again and practice it a lot, because this is like purely maths, not even physics. So yeah, anyway. So one by one we are going to do this. First of all, always try to solve the innermost circuit. All right, this is just a clue to you. So the innermost circuit is this one. So I'm going to solve this one first. And then when you get out of this circuit, you see that this is in series with this circuit. So basically this is a parallel circuit and this is a series circuit. So I'm going to solve this in the second step. And then these two are basically the third inner circuit. So we're going to solve this then. And after that, 2 and 3, these two are basically parallel to each other. So that would be my fourth step that I want to take. This is series, as I can see. All right. Is that clear, everyone? Aisha, Aman, Khatija, Ahmad?
Yes, sir.
Good. Now, the resistance of parallel would be, for the first step, what I'm going to do is I'm going to say 1 upon R equals to 1 upon 40 plus 1 upon 60. That's important. And in the calculator, you should always remember that there is 1 upon R, which means when you're solving this up, you should be like doing 1 upon 40 plus 1 upon 60, 1 upon answer. So it should be like, after that, why I do 1 upon answer, because then I have to take a reciprocal, that's why. So it is 24 ohms. So that should be the first one. All right. Okay, next. In the second section, so basically what I learned from this is that this whole part has a total of 24 ohm resistance, and now 24 is in series with 96. So what I'm going to do is I'm going to find it as 24 plus 96, and that's going to give me 120 ohms. So one by one I'm solving everything. In the third section, I have R equals to, in the third section, it's basically series, so it can be added directly, like 40 plus 20, so it's going to be 60 ohms. And for the fourth section, because now the third and the second section both are in parallel, so I'm going to write 1 upon R equals to 1 upon 60 plus 1 upon 120, like that. So again, you can use the calculator. Simply just do 1 upon 60 plus 1 upon 120, and then divide by 1 upon answer. So that's 40. So the total resistance is equal to 40 ohms, and that's what I got as my answer. So I have shown this. All right, so that's equal to R. Now, any questions, please let me know. Now, so the next part is equally important, and it says calculate the current in 60. So we want to find the current here. So how do we do that? First of all, I did not give it. This was 6 volts. First of all, I should understand that basically this network that you see, where 60 is, right? This whole branch gets 6.0 volts. That's why I wrote that basically the potential difference or the voltage given branch wise. Now I want to find the current here. So there are a couple of ways that I can do it. Okay. First of all, I would like to find the total current that is coming into the circuit. Like, what is the total current that was entering this? So I can use V is equal to IR. I know in this whole branch, the total resistance is 120. So the voltage is 6 in the whole branch, current is I, and the whole branch has the resistance of 120. So the current must be 0.025 amperes. So that's the total current. Now let's look at method 1 to find this. In the method 1, I would say that V equals to IR, the current is 0.025, the resistance is 24, so that's basically the resistance of this whole circuit, right? So the current in this whole branch is going to be 0.6 volts. And now simply because I have this current in the whole branch, I want to find the current in 60. So I'm going to use V is equal to IR. And the voltage here was 0.6. The current in this one I want to find, and the resistance is 60. So it means that it's going to be 0.01 ampere. Is that clear? The other method is basically the ratio method, which is basically easy, but you just need to remember what is direct and inverse ratio. Like for example, I know that for whole 24 ohms, which is the total resistance, the current I got was 0.025 amperes. Now what I'm trying to do is that what will be the current for 60 ohms. Now whenever something is inverse proportion, like current and resistance are inverse proportional, so what we do is we multiply the values in the front by each other and put them equal. So when you do that, 24 times 0.025, hello Mariam, how are you? Mariam, I'm extremely sorry for the fact that I forgot about you. I had to send links to many students today, and I completely forgot about you. I'm really sorry. Okay, Mariam?
No problem.
Alright, Mariam,
Yes.
can I
Can you hear me?
Yeah, I can. Can I take your class, can I take your demo class around 7:40 today p.m.?
7:30. Okay.
No, that's Pakistan time, right?
But
7:40
tomorrow.
today. Is it possible for you?
Because today I have to go after an hour. Is it possible for tomorrow around this time?
Yeah. Okay. For now, you can just see what we're doing. We're just finishing up for 10 minutes now.
Alright. Thank you.
So
Thank you so much.
basically, in inverse proportion, you multiply it directly. So 24 gets multiplied to this, and 60 gets multiplied to x. So when you find this, you will end up with the same answer that you had before. So that's how it works. So basically, what you need to understand is that whether you go through the formulas or the ratio, it should be the same. But if you know, if you want to go to the ratios, you should know whether it's inverse proportion or direct proportion. That's the only catch in here. Otherwise, it's pretty simple. All right, Khatija and Aisha and Hamad Aman, do you guys understand this?
Yes, sir.
Very, very good. Now, so the next thing we're gonna do, it's basically called the internal resistance. So Khatija and Mariam, we are almost at the end of the syllabus. We're going to finish it within this week, and then we're going to restart it, in the crash course from January 1st week. Okay, so you guys need to join then. This is just for demo, but you can continue studying if you want to, just study nuclear physics at the end. Now, internal energy comes from within the battery itself. The reason is that battery looks like this. If you go by a cell, it looks like this. Battery main stored energy is the chemical energy inside. I don't know if it's taught in chemistry anymore, but in my days when I was doing my IGs, I learned this too. For some reason, I don't know. So the main basically change in energy was when chemical energy would have to change to electrical energy, and with that process some of the heat was also released. Now this part which we do not want is the heat, and that's the loss of energy that we have to face whenever we are using batteries or any source like that. Okay, now so inside the battery we expect to have two terminals, like the positive and the negative, and then the loss is basically, for physics we just use small r, which we basically say that okay, there has to be an equivalent resistance, that's why there's a loss. So basically this is the housing of the battery, right? And within that battery we say that there's a resistance equal to small r, and there is the terminals. What you guys need to remember is that this section would give you the voltage that is lost, and this section, let me change the color, this section is going to give you the EMF, which is the total voltage that the battery supplies. Okay, and outside the battery, so if you connect a voltmeter outside the battery like this, so this part gives you the terminal potential. Terminal potential basically potential difference, or let's write terminal voltage, basically tells you what is the remaining voltage that you can use for the components to run. Okay, also called terminal potential difference. All right, now so according to what we've learned in in O levels, and basically O levels, you guys are young, so the total energy that was supplied comes from the battery EMF, goes into energy supplied at terminals when it comes out, plus the energy that was lost due to the internal resistance of the battery. Now the total energy is basically the EMF. The energy supplied at the terminals are the terminal potential or the potential difference, plus the energy loss is basically the voltage that was lost due to internal resistance that is in the circuit. So EMF is written as E, terminal potential is the current that goes out, so current into the resistance that's out, and here we have I times R. Now let me just show you quickly. So because current in a series circuit is the same, so basically you can take current as the common, so it will be R plus small r. So what are these R plus small r? Let me show you with the complete circuit. Okay, so when the circuit is completed, so here we have an internal resistance, and outside the battery we have the actual resistance that we have added. So this section is your battery, this is EMF, this is small r, this is capital R, and the current is I. So in this formula, I just want to tell you that R is the internal resistance. Of course, it is in ohms, and capital R is called as the load resistance, which means that this is the any appliance that you're basically using in this particular circuit to run. And I, you guys already know, is the current, and E is the EMF, electromotive force, right? The total voltage. Any question, please let me know. All right. Okay, from this point onwards, would like to we'll continue tomorrow, and I'll see you again.